Okay, so sorry for that and this mess up front here. Um, I'll probably shift my focus to back there. I'm going to hang out front here initially because I promised to do a quick demo of the bacterial system using Insight Maker instead of Vinsim like we did last time. So I'm going to try to do that. Of course, I'm going to hang around up here while the projector is in the back. So let me see if I can manage to do that without too much fumbling. If I can find, there we go. All right, so Insight Maker is an alternative we can use instead of Vinsim. It's an educational tool, but it's fully featured, fully functional. Might get a little slow for really big models, but for educational models, works great. It's modeled after a tool called Stella. If you go and create a free account, which is up here, so you can go to insightmaker.com, you can create a free account. You'll be able to log in. And if you've watched my little Insight Maker tutorial, then you've seen some of this before, but you can create a new insight up here, and it shows you this little tutorial, which I'm going to get rid of. And this screen that it's currently showing on Insight Maker, they've changed the interface a little bit so that it's a little bit more stylized. And they've added some nice features, actually features that were specifically developed for this class. So I had sort of made some suggestions, and eventually they said, okay, yeah, we'll add that. So for example, they never used to have the ability to directly draw causal loop diagrams, but that was something they added because in this class, we said it would be nice to draw causal loop diagrams. So for example, if you go to this little palette that's up here, it now has a template called Slate that's actually been designed to draw a causal loop diagram. So it's automatically sort of will draw the solid arrows, it'll get rid of the chart junk. And if you right click on the links, you can change to add pluses and minuses to indicate causal direction. So that's kind of a nice thing that they've added recently. So if I were to redo the class, I might just do it all in Insight Maker so we don't have to deal with all the kind of Vinsim headaches, but it is what it is right now. So if we want to do the bacterial simulation example, very similar to what we did with Vinsim. We go up to this primitive button up here, and it's got add stock, add variable, add converter. So I can click add stock, and it brings in a box variable like this. It says new stock, and I can go over here and I can change the name of it to bacteria. And I know that I've got a number of sort of exogenous things that I need to set, like I'll add a variable up here. And this variable, in which case I just double clicked on it to rename it. That's another way to do it. And I said before I had this average time between reproductions or something like that. So I can say average time between reproduction or reproductions. And I can create another variable, say over here, add variable. Oh, I think it might have created, accidentally created two there. So I'll get rid of this variable by right clicking on it and saying delete primitive. And over here, I can say average lifetime. And if I click on these things, then over on the right, I see a bunch of details that I can edit. And so over on the right here, it says value equals 0 for average time between reproductions. Well, I can set that to match what we did in the spreadsheet to 0.75. Now, by the way, those of you who are finishing up those two spreadsheet assignments, for those of you who are having any trouble with your formulas or whatever, if you haven't noticed, I posted the tutorial online that's linked in an announcement where I do effectively all of assignment D1 in Google Sheets, and then I export it to Microsoft Excel and show how you can clean up the charts in Excel if you are trying to create those things there. And the Google Sheets explanation I give really will work inside Excel too. So if you're having any trouble with your charts, or figuring out how to do that, I highly recommend taking a look at that little half-hour tutorial where I basically do pretty much all of D1 in real time. So, so if you haven't taken a look into that, take a look at that. You're on your own for the toilet assignment, but if you know how to do the bacterial assignment, the toilet assignment should be a breeze. So, I've got this average time between reproductions, and if I want to match what we did in the spreadsheet, I can create a variable called, say, birth rate. So I create a new variable up here. I'm going to move this guy out so it doesn't keep putting variables on top of it. And I can call this thing, let's say, birth rate. And likewise, I can create a variable here called death rate for the other side of it. And if I want to link these things together, there are up here, it says got flows, transitions, and links. So I can say which type I want to draw, which line I want to draw. Do I want to draw a flow or do I want to draw a link? And again, for those of you where it's a little small in the monitor in the back, if you'd like to log on to Zoom, and as long as you turn the volume down or off, or even you could just disconnect audio, in Zoom, you can say, don't connect my audio. Then you can follow along and you'll have kind of a version of my screen on your screen. So that's another option since the projector is dead. Maybe I can mute. I'm afraid to hit mute or whatever to turn this blue screen off. I'm afraid it'll turn that off. But so if I got links selected, if you mouse over these variables, you'll see a little arrow that shows in the middle of the variable. And if you click on that arrow and drag it to another variable, it'll create a link, a causal link or an information link, however you'd like to say that. So I can do that between average time between reproductions and birth rate. And I can also do that between average lifetime and death rate. Now, in order to get those connected to the bacteria stock, I need flows. So I can go back up to this thing where I recently just clicked links, change it back to flows, or they also call it transitions. And in that case, I have to, this is where it gets a little weird. This is the part where it diverges from Vinsim. I mouse over the middle of bacteria and I drag out of bacteria as if it's an outflow. So that works for the deaths one. So I can drag out this way and that will create a deaths outflow. And I can go over here and I'll just call it deaths. But my births, I want that, or reproductions, I guess I should call it since it's bacteria and not births, is that I want that to be an inflow. But when I drag it out, it looks like another outflow. So while that flow is selected, I have to go up here to this little reverse connection symbol and hit that. And it will change it for an outflow to an inflow. So just for reasons that have to do with how they implement this, that was just the easiest way for them to do the interface. Is you click on the stock, you drag out into the void, and it always produces an outflow by default, and then you flip it, and that's how you get your inflow. And then you can just rename that inflow. I'll call it reproductions. And then now I can go and change this back to links, and I can say that the birth rate, well, that will go to reproductions. The death rate, that will go to deaths. And bacteria, I'll click on the link in front middle of it, and that will go to reproductions. Now there, where'd the link go? This is another thing that it doesn't create a little arc by default. So I have to do something that is another Insight Maker specific thing. I'm holding down my shift key, and if I click in the middle of the link that I just drew, it puts a little handle there. Then I gotta let go, both hands off here, so that I don't have my hand on the shift key. Because if I do this next part while still holding down shift, I'm gonna get rid of the handle. So then I grab that blue handle without my other hand on the shift key, and I drag it up to make it a nice arc. I do the same thing where I put this in the middle of bacteria, go to death. Gonna again create one that I can't see. So I shift click to create a handle, hands off, pull it up. And now I've got all my links in play. So I got all my flows, all my links. Let me see if I can make this a little bit bigger. No, for this class, that's kind of a book thing anyway. So for what we're doing, no, it's fine. No, I think just links is kind of good enough. So sorry, I'm just kind of playing around with the zoom level here. And it doesn't look like I'm gonna get a decent zoom out of this. Let me see if I can. All right, that's good right there. All right, so now I need to update the formulas. So I already did under average time to productions, I put that as 0.75. Average lifetime, if I click on it, I can go over here. I can do 3. Now if I go under death rate, if I click on the value here, notice that right underneath it, it shows me average lifetime as an option. So it's showing me the linked primitives is what it calls it. So I can say Well, the death rate is just 1 divided by the average lifetime. Similarly, if I go to birth rate, I can click on the value and it says, oh, average time between reproductions is available. So 1 divided by average time of reproductions gives me the birth rate. Then when I click on the reproductions flow, under flow rate here, it has both bacteria and birth rate. And I know that my flow rate is just the number of bacteria times the birth rate. And similarly, if I go to death and click on the flow rate, I get number of bacteria times the death rate. Now, over here, notice it's got this little sum here. I've kind of been glossing over that, but if you click on that, it's got a bunch of mathematical functions that are available for you. So if you need to put any extra math in there, and we'll see that as we get further on in the class, but it's kind of a quick reference there. It's kind of nice. And then also notice there's this little expand box. If you ever need more space, you click on that and it gives you this nice big box to type in your expressions with the quick reference down the right-hand side. All right, now the last thing we need to do is set the initial condition for the bacteria. So if I click on the bacteria, and this is one thing that's kind of nice about Insight Maker, it's a lot less confusing than in Vensim. When you click on a stock, you got lots of formula options. But and I'm going to tell you throughout the semester, don't touch the integ. Let that be handled by Vensim. The only thing you ever touch is the initial value. In Insight Maker, that's the only thing it lets you touch is the initial value. So I'm going to, under initial value, set that equal to 1. Now, one thing that I do want to make sure is that allow negative is actually turned on. You might think that's weird. Why would bacteria I want to allow negative? If I have an error in my formulas, I want them to show up. And so if I turn off allow negative, Insight Maker is going to cover up my mistakes. So if I see negative bacteria in my plots, I want that to red flag. Oh, I need to update my formulas. But if I turn off the allow negative, then that can make it so that I think my formulas are working correctly, when in reality, they're not. So I want to make sure that even though bacteria is positive, always positive or always non-negative, that it has the option to allow negative. Similarly, when you click on the flows, it defaults to only positive rates. I'm going to turn that off because I don't want that to be only positive rates, because if there's a problem in my formula, I want it to be reflected. The downside of turning that off is in the graph, notice out here that now it's a double arrow where this arrow is filled and this arrow is empty. The empty arrow indicates the negative direction, the filled arrow indicates the positive direction. It makes it a little uglier to look at, but I feel more confident that if there's an error in my formulas, it'll show up in the output. So similarly for the outflow, I'm going to click on the outflow and turn off the only positive rates. All right, and that's it. So I'm ready to simulate. And so before I do that, are there any questions about how we built that stock and flow model inside Insight Maker? Yeah. Yeah. Mm-hmm. Uh-huh. Style? Yeah, well, so up here, that's a good question. That's advanced, but so under these styles here, you can create themes. And so you can go, so what she's talking about is if you like right click on these things, you can go and change all of the visual appearance that you want. And then after you've set that for one of them, you can then say set as variable theme, and that'll say all the variables that have not been edited are going to take on whatever you've changed here. After you've done that, if you want to, you can then create a custom theme. So up here, you could create, sorry, if I click on, if I get out, if I click on the white, if I click on this and go under like custom, then I can actually end up saving these themes. I think actually, this is off the top of my head, I forget how to save themes, but it is possible. It'll just take me a second to find it, or it'll probably take me after class to find it. But once you've done it for one, you can then save. You can say, this theme that I've saved, I want to create one. And then it'll show up under this themes menu as a custom theme of yours. And then you can just quickly go back to it. All right, so any other questions about this? Questions online? I'm trying to, this is not my normal control desk here, so trying to manage things. Okay, great. So now let's see how to run it. So I'll hit save, I guess, and I could just save it as, you know, a new insight or whatever. But if I want to run, it's over here. I click simulate, and it immediately draws the graph, and it's plotting everything here. So it's got bacteria, average time between reproductions, average lifetime birth rate, death rate, everything, things I probably don't need. And notice it's a little chunky. It's got these corners. So that's because I didn't do one thing that I should have done, and that was to change the time step. And so there's this little clock up in the upper to the top here where I do simulation time settings. And I can set this to, I want it to run for 5 minutes. And look at that simulation algorithm, Euler's method, like we've been talking about. And under simulation time step, that's my DT. It defaulted to 1. So I'm going to change that to 0.01. Hit apply. And then now, if I go and simulate that, then it does this stupid thing where it animates it slowly as if it was like happening in real time. And I don't know why they do that, but I think they just think it looks cool. I always just say full speed, and then it just does it as fast as it can, which makes more sense to me. Like, I don't need the drama. So, so this blue line, that's my bacterial growth. Looks like an exponential growth curve. And look at that, it gets to around 144, just like it does in our Excel spreadsheet, in our Vincent example, et cetera, exactly the same. And I got all these other things down here that I like to turn off. If I go up here and click on them, I can temporarily turn them off, so I can just see the bacteria. But I might want to just have a display where I'm only plotting a couple of things. Well, if I click add display, I can say that I want to see a new time series, and I can call this just like bacteria or something, bacteria only. And then under primitives, I can select what things I want to plot. And I'm just going to select only bacteria. And then I could say, well, if I create new primitives on the graph, do I want it to automatically do there? Do I want to show points, et cetera? Do I want to show areas? Do I want to adjust the time or the labeling on the axes? So that's all over here. And so there's a lot of sort of graphical things that I can do here. And then whereas the default display had all those plotted, bacteria only has the bacteria there. Now, unfortunately, there's no great way to export this as an image that you could, so you could screen capture this. That's one way to do it. But the alternative is, which probably is the preferred way, is to export the data and then pull them into a program like Excel, where you've got a lot more charting things. Because really, Insight Maker is not meant to be a charting tool. It's just meant to be a sim tool. So the way I get the sim data out is I click add. It's weird. It's called display, but I click add display. If I go over to the table, I can now say like, export data. And under primitives, I can decide on what I want to export. So I might export the bacteria. I could choose to export other things as well, but I'll just do bacteria as the only thing I want to export. And none of this matters here because it's not going to be a chart. And if I click apply there, it gives me a table. And you should recognize these numbers now if you've been staring at them enough times, is that we've got a time column just like in Excel and a bacteria column just like in Excel. And what's nice here is I can click download CSV, and I can create, I'll just call this bacteria data Insight Maker. And and then that CSV file, if I open up my Excel, or you could do this in Google Sheets. So I'll open, here, it's a little hard for me to see, but okay, open, choose my bacteria sim, and it opened it in my other screen. So let me drag that over. If I can figure out if my screen's on the left or right. All right, and then there it is right there. So if I were to zoom in a little bit, we can see those are all the data, and I could highlight all that data if I wanted to. So since it's 0.01 and I'm simulating for 5, then it should go down to about 500 rows. 501 because of the header. So 502, I guess, because maybe there's extra header. Oh, because of the initial condition. And then there I could do things like go and insert, and I could make my chart type. So I can say I want to do a scatter chart, maybe a line, and there's my bacteria. And if I want to add axes, I go to add chart element, and I can say axes titles. primary horizontal, and I can say that's time. And then I could do add chart element, axes titles, primary, oh, I meant to say primary vertical, but now I just deleted my horizontal, but I hope you get the idea. Primary vertical, I could say bacteria, and this is number of bacteria, and so on. Primary horizontal, time, and whatever my time unit is. And then if I want to make this only go to 5, I can click on the axis here, double click on it, go over to my axes data options, and under maximum, I'll set this to 5. And there we go. So now I've got a simulation data generated by Insight Maker instead of by Excel or Vinsim. So that's an alternative to using Vinsim, and of course, Excel or Google Sheets. So any questions about that? Using Insight Maker to do stock and flow. Some people like Insight Maker, some people like Vinsim. For the rest of the course, I'm going to try to do examples in both, and just go with whichever one you like. If you don't like Insight Maker, that's fine. An advantage of Insight Maker, sometimes it might be easier to share your models when you get your final project groups, but Vinsim can work fine too, depending on how you compartmentalize your work. So, questions online? Okay. All right, so with that, let's shift to the regularly scheduled programming. All right, good. So I'll try to float around here, maybe to the back of the room. I guess I could play around with the camera angle here. If it will go, well, it's probably not, it's gonna have like a bar in the way if I do that. All right, well, this is just gonna be awkward and we'll just deal with it. All right, so modeling dynamic systems, this is Morecroft's take on stock and flow models. So hopefully this will look familiar from what we've worked on so far. So stocks and flows, drawn a little bit like this, kind of gone over this already. The stocks are the things that keep track of where the system is. The flows are what makes it change over time. So flows make stocks change over time is kind of the key point that I hope we're kind of seeing here. So they had this example with instructors where we're saying that in a university, you could have some pool of instructors, maybe you have instructors, tenure track faculty, tenured faculty, whatever. So, you've got a network of these things, and you've got an inflow process, which is like a recruitment process, hiring them. But for various reasons, retirement, maybe they get job offers out other places, you have some turnover process. Now, other things could be determining the recruitment process or the turnover process. The key point here is that we don't ever directly interact with the stock. We interact with the stock's flows. And so the thing that makes the instructors grow is recruitments. The things that makes instructors decline is turnover. And so those are the things that we interact with. So whenever we see one of these stocks, we need to specify an initial condition. So we can say initially there are 0 instructors at the university. Behind the scenes, and this is a formula you never need to report to me, but Morecroft always has it in there. This is Euler's method, basically. So this is what we manually implemented inside Excel, but you do not need to report that to me because that is what goes on behind the scenes in Vinsim or Insight Maker. But Morecroft's just showing us here so that in case we didn't know what was going on behind the scenes, that we would see that, okay, this is how it's being updated. We have a small DT, and so we've got instructors from the previous step is going to be, you're going to add that, all the inflows minus the outflows, multiply that by DT, and then that's going to give us instructors at the next time step. So we're just seeing exactly what you guys have manually done in Excel, just written out for us. Now, if to see the relationship to calculus there, you can take this formula, this Euler's method formula here, rearrange it, so you move the instructors back to this side, divide them by dt, and I hope that looks to you like an approximation of a derivative of this instructors function. And so basically, if we make dt really, really small, so that our simulation time step goes on very, very tiny steps, then the function that we get out of this process will approximate the real function that is determined by this mathematical expression. So that's what we're trying to do, is like not solve this directly, but approximate its solution through this little stepwise process. And that's what we call Euler's method. It's an approximation method. So really what the sim is doing is it's solving this initial value problem where instructors at any time is whatever the initial instructors are, plus the integral of the inflows minus the outflows over time. So that's the connection to calculus. But we don't need to do any calculus in this class. I just want you to recognize that all of the graphs that you see could be described by formulas that we could, in theory, solve using analytical methods, but we're using numerical methods. We're using the computer to approximate them instead. So if I look at this graph instead of the differential equation, I see the inflows show up down here as all the positive terms in this derivative, and the outflows show up as all the negative terms in this derivative. And so the net flow is just the sum of the inflows minus the sum of the outflows. And that's all that's being depicted up here. It's just a way to write this expression graphically. Okay. And that's all that's kind of shown there. So with that in mind, if I think about this formula up here, if I try to conceptualize what's going on here, if the recruitment minus turnover, that net flow is constant over time, then what would we expect the instructors to look like? So in other words, if this thing inside the integral is constant, what would I expect the shape of this thing outside the integral to be? What's the integral under a constant? Like if I'm integrating 5, what's the integral of 5? Does anybody remember? So 5 is in there, but if the integral of a constant, so it's like the integral of 5 dt. Go ahead. What would I didn't hear? So if we're integrating a constant, we're going to area underneath the constant, and so it's just going to be the constant times time. So if I take the integral of 5 d tau from 0 to t, that's just going to be equal to 5t, right? Because if I take the derivative of a line with respect to time, I just get 5 out. So if I take the integral under 5, I get 5t out. So, so this is a flat line. This is a ramp. Okay, does that make sense? Yeah, I'm not going to ask you to do any calculus on the midterm or anything like that. I just want you to start seeing that the graphs that we get aren't arbitrary, that in theory, the graphs that come out of this stuff really, we could find in other ways mathematically, but this is a shortcut to it. All right, so how does that show up here? So Morecroft's got this example where he's got, it's hard to see because it says I'm talking, but turnover is line 3, recruitment is line 2. Those are the outflows and the inflows. And instructors, that's the stock, is line 1. So it says that turnover, the outflow is 0. It says that recruitment, the inflow is 2. The difference between them is constantly 5. And so this line 1, that's the integral of 5. That's 5t. If I were to go 0 over about 5, which is around here, it'll go up 1. So it has a slope of 1. So this is just taking the integral underneath the net flow. That's how I get that straight line. So the constant net flow gives me a rising stock. So it's like a bucket that the net flow into the bucket is positive. So the bucket over time keeps rising and rising and rising. That's what's happening, is that because our recruitment is greater than our outflow, then the number of instructors at the university keeps rising and rising and rising. Does that make sense? If I have a constant net flow, I get a rising stock over time. It's like a bucket analogy. All right, I'm going to back up and see if there's any questions online here. Okay, I think we're good. And maybe I'll tap here to make sure. Okay. Okay, so let's getting a little more complicated then. So now I've got a movement through 4 different net flow conditions. So I'm saying that there's some exogenous force that's changing the outflow characteristics. So it's not determined inside the model. The simulator just says that after about a year, we go from having no one leaving the university to suddenly having some rise where people keep leaving the university. And then after a year of that rising up, it levels off and people still keep leaving the university at a constant rate that's higher than the recruitment rate. We don't know why. That's not being specified here. We could create an extended model that would simulate, maybe internal reasons why this could happen, like, maybe it gets too crowded at the university and that causes people to start leaving. But we're leaving that out of, we're just saying there's some reason this is happening. So what happens to the level of instructors? And that gives us these 3 regions. And the first region is the region we just handled, where we have a constant recruitment that is greater than the turnover. And that means that in this region, we get a line. But at the instant the the turnover starts rising, then the area between these curves, so you can think of this as the difference, I'll say the difference between these curves, that starts changing as well. So the recruitment minus turnover is high, but it gets lower and lower and lower. It hits 0, and then it goes into the negative. So now the net flow starts positive, and it is a line that gets negative. So now we're integrating under a line with a negative slope. And if you integrate under a line with a negative slope, then you're going to get this quadratic here, which is like minus x squared, basically. And so the idea here is that in these 2 regions, this is all integrating under the same line, but here, this is when the line is still positive, and then it hits 0, and that's where this thing reaches its max, because the derivative is equal to 0, and then it starts going negative. So all that stuff, if you remember from calculus, if I want to maximize a function, I take its derivative and set it equal to 0. That's what you see, the net flow being equal to 0. That's when line 2 is equal to line 3. That's when the net flow is perfectly balanced. The recruitment's perfectly balanced by the turnover, so the net flow is equal to 0. And because of that, the corresponding stock is maximized. So it's just calculus, just with this fancy numerical approximation instead. And then when it levels off, now I've got a region where I have a negative outflow that's constant. So this just means that the turnover is constantly greater than the recruitment by the same amount. And that's why this is a straight line going all the way back down. So that's how I get this funny, even though the inflows and outflows aren't changing that much, I get this interesting curve shape. It's just the integral effectively in between these 2 lines. So if I the area in between 2, like 2 minus 3, it's that area there that I'm adding up. And so that area kind of disappears, and then it becomes negative. And because of that, then I get growth, and then I get decline. All right, so there are questions about that interpretation. Is it clear how these changes in inflow and outflow lead to this hump-shaped growth and decline of the instructor's stock? Now, if you know the flows, you know what the stock is going to do. Check online to see if there's anything. Okay. Okay, good. So, so what I'm trying to drive at here is that despite how annoying calculus might be, then if you so it was sort of all that was available when Newton and Leibniz were around when they developed calculus. But imagine if somehow you were to give Newton a computer and allow him the ability to use numerical approximation. It's possible we would have never gotten calculus, because you can answer all of the same questions with these simulation results. So if I think about an apple, so I've got an initial upward, so I throw an apple up, it's got some initial upward velocity, and I like to describe how high the apple gets over time. So eventually it goes up and it comes back down. And so Newton said, well, you know what? There's gravity that's coming back down. So he says that the change in velocity over time, acceleration, that's equal to negative gravity. And well, I can draw that formula there. The change in velocity over time is equal to acceleration. Acceleration is equal to negative gravity. I can draw that as a stock and flow diagram. I can say that I can have a velocity stock that's changing over time. Its flow is acceleration, and I can set the acceleration equal to an exogenous parameter called acceleration due to gravity, negative g. Likewise, the position I can describe as y here, and there's, I don't think I can unfortunately move on the Zoom rooms screen here, our room away, but this dy dt, that is equal to v, is all I'm saying here. So the change in position over time is equal to velocity. And I can just as well represent that as a stock and flow diagram. I can say the stock apple height is equal to this stock here. Its flow, the change in height over time, is exactly equal to velocity. So Newton found a way to say, okay, I described the world this way, and I'm going to figure out the math to solve for the expression to make this, to figure out what the position is over time. And so with calculus, formal calculus says this is the position of the apple over time, this expression here. But if I would have just drawn this in a simulation and hit play, then this blue curve is also the position of an apple. It tells the exact same story. And if I plot this y, I will get exactly this blue curve. If I plot this v, I'll get exactly this red curve. And maybe it's more informative to have these formulas, but it's not that much more informative. So, you know, if we have the ability to do this thing down here, we may not ever need this thing up here. And in reality, it's hard to go from this expression over to here for a general set of systems. But it's pretty easy to go from the same set of systems to the approximation here. So we have the ability to describe the behavior over time of a wider range of systems than the mathematicians can do by using these approximations, which is why I sort of think that if Newton had access to a computer, which sort of puts the cart before the horse, but you know, just go with it here. If Newton did, in a hypothetical world, somehow been given access to a computer from the future, I don't know if we'd ever actually get calculus. Just don't know if it would be useful at all. And I think a lot of times we hang on to calculus just because people like it. So it's just a thought. So any questions about that, about stocks, flows, derivatives, things like that? Or these kind of fundamentals? Questions online, chat. All right. Okay, so how do we build these things? This is a little bit like building the causal loop diagrams, but causal loop diagrams are really meant to be complementary to these things. They're not sort of replacements. And someone pointed out in the reading that some of these are gray and some of them are black. As far as I know, that was just a weird typesetting thing, or this graph was actually borrowed from a paper that Morecroft wrote. And in the paper, he might have actually been highlighting the things on the left or the things on the right. And that's why there's a difference in color, but he's not in the book. So don't pay any attention to the difference in colors there. But I do want you to pay attention to his definition of tangible stocks versus intangible stocks. Tangible stocks are the ones that are easiest to define. They're the physical things out in the real world. The number of staff currently employed, the number of studios at a TV station, the number of correspondents, the number of transmitters. These are physical things we can walk around, we can bump into, we can touch, we can pick up, we can count. Those things are definitely important. But there are intangible stocks too. And these are just as important, but you can't really count them. Like, you know, maybe the number of languages, that's something that maybe it feels kind of countable, but it still doesn't exist in the physical world. Program quality, that's another thing that we can survey people, but it doesn't exist like in the real world. We can't pick it up, you know. But we do know that as a TV station's program quality increases, it's going to change you know, their income streams, which will change the number of transmitters they own, which will change the number of correspondents that they can purchase or they can pay. Likewise, the number of languages that are on a TV station. As you get more languages, you can go into more markets, which will mean more correspondents, more transmitters, or whatever. So if you don't include these intangible stocks, in your bookkeeping, you'll miss a major part of the dynamics, and you'll have to sort of say there are these weird exogenous variables that we just don't understand. When in reality, if we have those in our system, we can explain a lot of the variance we see. So when you come up with stocks, it's not just the stuff that you literally can be poured into a bucket. It's everything that could possibly change over time that we could maybe think about putting on an abstract, sheet of assets. So think of them as the assets. And if you really think about it, all of these things, so if I go back to trying to see, well, yeah, if we think about all of these four things plus these two things, those give us all of the assets that are necessary to describe this TV station. So are there any questions about that, the difference between tangible and intangible stocks? Does it make sense that we need variables to describe both of these things? And because that little guy showed up there at the bottom, I'm going to make sure that there's no new. Oh yeah, thanks. Thanks, Derwin. I appreciate that. All right. Yeah. Yeah, they're things that don't have physical form, but they still need to be accounted for. So we can't count them by looking at them, but we need to count them. So we need to keep track of them. Well, I mean, if you're so the question was about a calculating. If I can calculate it from other things in the system, it's probably not a stock. It's probably a variable. But if it is something that is an independent degree of freedom, I need to account for it. So that's really what a stock is. It's an independent degree of freedom that will be coupled to everything else as you move through time. It has to be able to be measured so that I can create a model of it that so like program quality, I need to be able to put that on a scale from 0 to 1 or whatever. And then as the program quality moves around, I'm going to need to be able to convert quality into things that affect transmitters and all of the rest of that. Now, somebody else could have built a program quality scale going from 0 to 100, and I would have to arrange that. So yeah, there's going to be questions on what units to use and how to measure them, and whether it's a linear scale or a log scale or whatever. But those are usually mathematical things that we can work out. As long as we have a way to, it's almost like in causal loop diagrams, as long as it's sort of measurable or sortable, then it's probably something that could fit into these things. All right. So any other questions about that? So along with stocks, then we also have to come up with flows and links. And the links are what bring everything together so that things are just floating independently from each other. And that's what Morecroft will call throughout the book coordinating networks. So that was, I think, something we looked for on one of the reading exercises. And so we've got our stocks, we've got our flows, and then down here we've got these converters, which sort of convert from one quantity into another quantity, possibly into another quantity, until it's compatible to be used in a calculation of a flow. Notice that none of the links terminate on the stocks. That's really important. Links always go out of stocks. They never go into stocks. The only thing that goes into a stock is a flow. So flows, converters, and links. And don't worry about the difference between causal link and information flow. You can just think of them all as giving access. And so this formula needs access to this stock, and that's what that line is for. This formula needs access to this one. And that, I think, is what I've got on this next line here, is that if inside here I've got an equation that is some formula that's a function of B and C, I got to make sure that B has a line going into there and C has a line going into there. And tools like Vensim and Insight Maker, when they give you the little shortcuts for what variables you can use, they only give you variables that have the links coming into them. So they make it easy for you to think like, oh shoot, I want this formula to depend on this. It's not available to me. I better go and draw that line before I put this formula in. And if you try to write the formula out before putting that line in, then both of the tools will give you an error. So any questions about the coordinating networks? In the stock and flow, in the causal loop diagram, they're about understanding causality. In the stock and flow diagram, it's about giving access to information from one point to another. You can generate causal loop diagrams from stock and flow diagrams, but these links sort of serve slightly different purposes. They're closely related. Okay. All right, because of that, sort of moving a little bit faster through here, and I apologize for that. That's due to this weird technical thing with the blue screen behind me. All right, so the other thing, this is a Morecroft thing. It's not necessarily something you'll see in a lot of other references, but I think we usually see something like that. When we start building really big models, it seems daunting to try to build all of those stocks and flows all at once. And so what Morecroft introduces are these sector maps. I think everybody does something like this. Morecroft calls them sectors. You could call them a bunch of other things too. But like in VinSim, there's views, and in Insight Maker, there's folders. And views and folders in VinSim and Insight Maker, respectively, are how those two programs implement sectors. So everybody's got some version of this. They just call it something different. But I like Morecroft's term sectors because it seems sort of like software agnostic. It's basically this idea that everything's interrelated, but some things are more tightly coupled than others. So it's possible that, community is going to affect police department. Police department's going to affect the street market for drugs. That's going to affect the world of the drug users, and that will affect the community. But there are a lot more links inside the police department than there are across, a lot more links inside community than there are across, and vice versa. So rather than trying to build everything at once, it's easier to just build a police department, and anything going to the community, we pretend like it's an exogenous variable. And then we build community, and anything that's going out to police department, we just think of it as an output. And then we combine all of those together. And so that's what we've kind of got here. It's like a causal loop diagram is too little detail. A sector map kind of is in between that and a stock and flow. And so if we were to break each one of these four sectors up, and I'll zoom in on some of these here, then each one of these sectors looks like a relatively simple stock and flow diagram. And if I look really closely, I can see things like up here, I'll just read it from back here. Up at this top thing, this says call for police action. And if you note, it's also repeated here, call for police action. So this is the police department sector. This is the community sector. So I've seen variables show up in multiple sectors. Well, in VinSim or Insight Maker, those variables would be the same. But inside VinSim or Insight Maker, I can actually put this on one sheet, this on another sheet, this on another sheet, and this on another sheet. And I can define some variables as existing on multiple sheets simultaneously, effectively connecting them together as if there was one big network. But when I edit them as if this is the only thing I care about at one time, just the police department. And that makes it much easier to build these models, and sometimes easier to analyze these models. The downside of this process is if there's a feedback loop that crosses sector boundaries, you lose it. So you don't see it. So if there's a feedback loop that goes from here to here to here to here, it might be a lot harder to see. But that's why we usually try to break sectors up so that there's very little integration kind of across sector boundaries. So most of our feedback loops happen within the sectors. That way we don't miss a lot of feedbacks that go back and forth. And so just if I want to zoom in on that, like let's say I want to build the police department sector. So in the police department sector, I have a little stock, a number of police allocated to drug busting. I've got the flow, the change in the allocation, and then what things affect that flow? Well, there's the number of police officers I would like to be on the street working on drug busting. And there's the time it takes to actually get them to go from rookie, or to get them from cadet stage to rookie to actually being out onto the street. So the time to actually educate these and bring them into play here. And then there's the actual number that are out there. So those are sort of the important variables here. So if I think about the units here, this stock is in police officers, this stock is in police officers, this stock is in months because it's time, and this flow has got to be in this stock's units per unit time, and that's why it's in police officers per month. So if I want to figure out the formula here, I've got to combine these three variables in a way that produces this unit, police officers per month. And none of these are police officers per month. So that kind of tells me there's probably going to be a division going on. I'm probably going to do something with these two things to produce a police officers. I'm going to divide it by this thing to produce a months. So just looking at the units gives you a hint of what the formula should be. So let's try to think about that. So what's the change in the allocation of police officers? Well, this is just a reminder of kind of Euler's method here. The change in police officers times dt, that's what gets rid of the month, and that's how you get the difference in police officers and months. But I wanted to zoom in to say, well, how do I actually form this formula? How do I get the stock divided by time? Well, if I think about it here, if I do the difference of these two, where this is my desired number of police officers, and this is the actual number of police officers, this quantity here tells me how many police officers that need to be added, or it tells me how many too many police officers might be out there. But let's assume that I'm just trying to grow the police force on the street. This tells me how many I'm lacking. And then if I think about it, this is very similar to the tank gap in the toilet model. So it's kind of like I've got an indicated number of police officers. It's not trying to say anything disparaging about police. This is, but it's just saying dynamically it's the same. The target water level is like the indicated number of police. The water level is like the number of police actually on the street. And so the difference here, this is like a tank gap, but in terms of police officers. So then I have to figure out what's on the other side of it. Well, the time to move staff, that's how long it takes to actually get a new police officer available. And so we can think of this as the average time it takes for a police officer to move into drug busting. So some police officers will be promoted more quickly, some will take longer, but the average police officer will take this long to move into that. And that's actually kind of similar to our time constant in our toilet model here. So if we think about our toilet model, it was gap divided by time constant. Well, that's exactly what this is here. It's our gap in the number of police officers we want, divided by the average time a police officer takes to go from not being ready to being ready for this switch. And that tells us the rate in which we'll get a change in police officers there. So even though the indicated allocation changes instantly, like when you flush a toilet, suddenly you go from needing 15 centimeters of water. Well, you're not going to get it immediately. It's going to take this time constant to get there. So regardless of how quickly the community's needs change, police officers on the street are going to be slowed down by this time constant. And that's what we're modeling here. So that's how we build that. And then check the units. Police officers divided by month. Well, that is, as we needed, police officers per month. So that's how we built that formula. So that is a model of how we change police officers over time. So are there questions about that? Does that analogy with the toilet tank make sense? Okay. So that's how we get our flow. All right, so other things like how do we figure out what drug seizures will be? Well, this is supposed to be in kilograms per month, but if I look at up here, the thing that's going into this is police officers. So that's a little bit weird because there's no kilograms or months there. But then there's this exogenous parameter, police effectiveness in drug busting, kilograms per officer per month. Well, there's my kilograms, there's my month, but there's no police officers there. So already, without sort of thinking through the logic, I kind of get a hint at what the formula must be. If I were to multiply this thing by this thing, the officers are going to cancel and I'll get the right units. So that's what I might try here. So I'm going to say, well, I've got kilograms per officer per month. I got police officers, multiply them together, I get kilograms per month. And so drug seizures, I'm going to try as police effectiveness times number of police. And actually, that kind of makes sense. And if you think about it, that's a lot like our births formula and deaths formula in the bacteria. It's kind of like the number of bacteria, and it's their effectiveness at making new bacteria. That's like their birth rate. And so that's kind of a way that I can say that, this is how much, these are how many kilograms each police officer can pull off the street per month. This is my number of police officers. So with this police force, this is how many kilograms we can pull off the street collectively together per month. So does that make sense? That formula there, relatively simple formula. Any questions about that? So like on a midterm, you might imagine I could give you some of these sort of things, right? Give you the units or whatever. And I'd say, all right, so this is supposed to represent this. And I give you sort of a description. Here are the variables that must go into it. Here are their units. I might even give you a partial form of the formula. What are acceptable formulas that would make sense for this? And so that might be based just on the units. And so you could go through and you could exclude the ones that have the wrong units. And if there were two that had the same units, then you could try to use some sort of logical reasoning to say which one actually makes sense based on the description of the system. Okay. All right. So the only other thing I kind of want to cover here, and I'll do this kind of quickly, but I thought these are some nice examples here at the end where they talked about these anomalous behaviors that indicate that there might be something wrong with our formulas or the simulation. And so when he ran the simulation of the police department at first, then there were two apparent problems. The one problem they had is that the supply of drugs becomes negative, and a supply should never be negative. So supply of drugs is this line 2, and at this time here, it goes negative. So even though there were 0 drugs, the police kept finding drugs, and so they went negative. And similarly, the street price grew unrealistically high, which made negative drugs out there, I guess. So we need to fix those two problems. So the first thing we can say is like, well, what might be causing it here? Well, the first assumption, police are equally effective at finding drugs, regardless of how many drugs are available. So this is the big problem for why drugs go negative, is that even though there's like 0 drugs out there, the models police effectiveness as an exogenous parameter. It's set outside the system. We're saying regardless of how many drugs are out there, police are just as good at finding them. So we need to connect the number of drugs to the police effectiveness so that as you get fewer drugs, police become worse at finding them. So that's what we're going to do, make drugs harder to find at low abundances. So if drugs are infinitely elusive at low abundances, the stock will always be positive. So the way you would implement that is you connect drug supply to police effectiveness, which is right here. And you could then make police effectiveness become closer and closer to 0 as drug supplies becomes closer and closer to 0. So that might require a sort of more sophisticated formula, and it might require some data to figure out what the right model is. But that's the big problem, is that this is a constant, but we know in reality, the police should become very ineffective at finding drugs when there are no drugs to find. And so that's the one big problem. The other problem we have is that the total supply of drugs is constant. So there's a fixed amount of drugs per month. So as a result, the supply of drugs on the street can crash to 0, causing the street price to grow without bounds. Now, in reality, we can actually make the total supply of drugs pay attention to the price of drugs. And so as the price gets high, then we'll get new suppliers come in from outside, injecting us more drugs. And so we, instead of assuming drugs are constant over time, so allowing them to effectively go to 0, as they go to 0, the price will go up, and then suddenly there'll be new drugs that'll be added in. So that's the solution. We could create a flow in this total supply for drugs here. It's currently a stock that has no flows coming into it, so it's just constant. We can actually now have an inflow coming into it that's based on the price of drugs. And so from the price of drugs, we can then actually create an inflow where as the price gets really high, the supply of drugs grows, which will end up reducing the price in the long run. and that makes more sense from from that perspective. So we use the graph. Hopefully it makes sense. And if we go back, we build a simplistic model. We ran it. All models are wrong, or some are useful. We knew it was going to be wrong, but over here on the right-hand side, we can see it's too wrong to be useful, because there's no universe where we have negative drugs, and there's no universe where the price is going to go to infinity for drugs when it's relatively easy to make drugs and bring them in. So we make those changes, and that's where we're done. So any questions about those, what do we mean by using anomalous behaviors to drive future iterations of your model? Simple. Don't worry about not getting it right. Use the way it's wrong to tell you how to make it more right in the future. That's kind of the lesson. All right. I don't think there's any questions online. Doesn't look like. All right. So, and sorry for the rush today. I'm going to try to submit a ticket about that thing. Just kind of announcements here. So after the midterm, we'll be reading chapter 6, but that's like way after the midterm. So unit E is what we do after the midterm. But if you want to, you can get kind of started on that. We're going to skip chapters 4 and 5, but chapter 5 might actually be useful to skim over when you're studying for the midterm. Like I mentioned in the announcement, you should start forming your final project teams. See the information on Canvas. There's a video that's posted. We want 3 to 4 member teams. Project proposals due a week after your teams are formed. Your teams are basically formed a week after the midterm. Due on Sunday nights, the muddiest point, and that assignment D3, the VinSim toilet model. The next lecture is going to be the midterm review. That's on Thursday. And then next week, Tuesday will be the stage 1. And then Thursday be the stage 2. And I actually went and changed the availability. You'll be able to do stage 1 Monday, Tuesday, and Wednesday. And stage 2, you'll be able to do Thursday, Friday, and Saturday. But it ends the Monday, Tuesday, and Wednesday will end at like 11:59. It won't go to 10 a.m. the next day. And then the Thursday, Friday, Saturday will go to 11:59 on Saturday. So you have a full 72 hours for stage 1 and stage 2, but stage 1 is timed, stage 2 is not. So and we'll go over all those details on Thursday. So bring your questions on Thursday. If you're driven all by questions, that's great. Otherwise, I've got kind of greatest hits that I'll kind of show in this lecture. Definitely take a look at the midterm review module. I got a lot of stuff like sample midterms and so on. All right, so if any other questions, I can take those after class. In the meanwhile, let me put up an attendance exercise, since I didn't do one last time, and I think I just got my mouse back. If I can just, maybe I'll do this. Resume. All right, so I'll put the so the question I'll have here for the Zoom is, we'll say, what is the only thing that you specify within the formula of a stock? So I mentioned that stocks are special. They're confusing in VinSim, but they're a lot easier in Insight Maker. There's only one thing that you configure in stocks. And so you leave your hands off everything else. So what's the one thing that you have control over in a stock inside VinSim or Insight Maker? That's my attendance question. Otherwise, that's all I've got for you. So again, if you have any questions, feel free to come up. Otherwise, we'll see you Thursday. Sorry again for the technical difficulties at the start of the class.